Welcome to another of our lecture series on our YouTube channel. And this will be a short lecture series consisting probably of 4 to 5 videos. And in this lecture series, we will talk about the theory of columns. So this theory of columns is a chapter in your course of strength of materials, probably the last chapter. And in this theory of columns, we will be looking at 4 or 5 different topics. You can see the course content on the screen. We will look at the theory of columns according to support systems. We will look at what is critical load. We will derive the Euler's formula for long column and see its limitations. We will also see some formula for intermediate columns. And one of the primary topics that we will be discussing in this series is the column behavior due to buckling. So today will only be an introductory class, and in today's introductory class we will only see the concept of stability of equilibrium in relation to a column. And from our next lecture onwards, we will start with the derivation of Euler's formula, and then we will go into detail about the behavior of column due to buckling. So let's start with today's introductory lecture. So in today's lecture, we will mainly look at this concept of stability. We know that when we are designing a structure, we are primarily concerned with two aspects. One is the strength of the structure, and another is the stiffness of the structure. The different parts of our structure may fail due to different conditions. For example, due to excessive load on the structure, or due to excessive deformations, or due to change in the configuration of the structure. So when we are designing a structure, these two things are kept in mind. This strength is the ability of the structure to support a specified load without experiencing excessive stress. That means the stress in our structure should not exceed the allowable limit, and if that stress that is coming onto our structure is resisted by our structure, then it is said to possess this property of strength. Whereas stiffness is also again the ability of the same structure to support that specified load without undergoing unacceptable deformations. So the deformations of the structure should also be within the allowable limit. Besides these two concepts of strength and stiffness, there is another concept of stability. Let us say this is our third concept. So what is stability? Stability is again the property or the ability of a structure, and that ability is related to change in the configuration of our structure. So stability means the ability to support a given load without experiencing a sudden change in its configuration. That is the stability. And we know this concept of equilibrium of a structure. So when we solved the problems relating to the static equilibrium, we used this concept: the summation of forces in Fx equals to 0, the summation of forces in y direction Fy equals to 0, and the summation of moments about z-axis equals to 0. So whenever we had any object in the xy plane, for it to be in equilibrium, or particularly the static equilibrium, then these three equations had to be satisfied. So what is stability of equilibrium? Simply saying that your object or your structure is in equilibrium does not give us much information. In fact, we have to check for the stability of equilibrium. For checking the stability of equilibrium, you can see three different cases now on your screen: stable equilibrium, neutral equilibrium, and unstable equilibrium. In the first picture here, you can see that you have some sort of surface here which is concave upward. This surface is concave upward, and the surface in the third figure, number C, is convex upward. So we are looking at three cases of equilibrium here. In the first case, you can see that a ball is placed in this position here. This ball is placed on this concave upward position. And what happens when you give a small displacement to this ball? That means either you displace to the right hand side or you displace to the left hand side. What happens when you give this displacement? This ball, after some oscillations, will return back to its initial position, which is the position at the valley of this, or the bottomest part of this valley. After some oscillations, depending on the frictional force between the contact area between this ball and the surface, this ball will return back to its original equilibrium position. This is the case of stable equilibrium. The ball will return back to its original position. In contrast, if you look at this third case, unstable equilibrium, you can see that this ball is placed at the top of this surface, or at this highest part. That means we have a convex upward surface here, and at the topmost part we have placed this ball here. So what happens to this ball when we give it a slight displacement either to the right hand side or to the left hand side? In contrast to our case number 1, when the ball returns back to its original position, this ball in the third case does not return back to its original position. In fact, it will have a tendency to go farther and farther away from the initial equilibrium position. And this case is the case of unstable equilibrium. The ball is in equilibrium in this case also, but when you give a slight displacement, the tendency is to move away and away from your initial equilibrium position. We call this unstable equilibrium position. And the third case is neutral equilibrium. You can see the ball is now placed on a flat surface here. And when you give a slight displacement to this ball now takes another equilibrium position here and remains in that position. It neither tends to move towards the original equilibrium position, nor does it tend to move further and further away from the initial position. In fact, it will just remain in equilibrium in that second equilibrium position. So if this is the first equilibrium, initial equilibrium position, then this is another equilibrium position. This is the case of neutral equilibrium. So in fact, our equilibrium, as we have seen now, may either be stable, unstable, or neutral. So how do we relate this to the analysis of our columns here? So before going that, as you know, our columns are moment resisting structural parts. These primarily resist axial compressive forces and also resist the bending moments. Columns are primarily vertical structures, and these resist axial compressive forces and bending moments. So let's relate this concept of stability in the case of columns. Now you can see here, we have an idealized column placed here. First, let us talk about this image, what is happening here. We have a column here, AC, and this AC is composed of two parts, AB and BC, the length of which is L by 2 and L by 2. So the length of both parts AB and BC is L by 2. This A is pin connected here at one end, and there is the roller at the other end. This means this joint C can move in the vertical direction. And also, these two parts AB and BC are connected at the center by another pin joint. And also at the center, there is this torsional spring. You have seen here, this is the torsional spring with a spring constant of, in this figure, the spring constant is given as beta r, but for our simplicity, let us assume that The spring constant for this torsional spring is K, or you can also say that this is rotational stiffness of the spring. Let us assume that these two rigid bars are massless. And you can see an axial compressive load P is acting at the top, and this P is acting concentrically with the axis of our members here, AB and BC. For example, if this is the vertical axis of our member, then the line of action of this load P coincides with the vertical axis of this member. Also, if we suppose that these rigid bars have a rectangular or a square cross section, this P is acting somewhere here at the very center. So the axis of these two rigid bars and the line of action of this force P in the given plane coincides. So now what would we like to do here is, currently this column is in a position of equilibrium, and let us say that at the very mid portion B, where we have this pin joint, we disturbed this equilibrium position of our column and gave a slight displacement towards the left hand side, as you can see in the second figure here. Let us suppose that our displacement towards the left is so small that this angle that the rigid bars make with the vertical line is very small. So we can write this theta angle as delta theta also, considering that these angles are very small, since our displacement or deformation given to this column is also very small. Let us try to make a free body diagram of this upper part here, BC, and let us analyze this. So we have taken only the BC part here. If this is the original axis, then this is the displacement that we have given to this part or given to this system here. The angle, let us say the angle made by this rigid bar BC with a vertical is delta theta. Now what happens is that in this free body diagram you can see two couples here. One couple is being formed by these two forces. Okay, let us continue again. By drawing the free body diagram of this part BC, we can see that there are two couples that are acting here. One couple is due to these forces P here. And these two forces, the distance between which is this displacement that we gave to the bar, these two forces are generating a clockwise couple. That means this couple in this way. This clockwise couple that is being formed by these forces P and P here, this is taking our rigid bar further and further away from the initial position. So we call this couple as disturbing couple. Whereas another couple is this moment MB here. And this moment is generated due to the spring that we have placed at the very center, that is this position B here. So when we give the displacement to the center of this system here, the moment due to the spring generates a restoring force that tries to bring this point back to its original position. So this couple or this moment is known as a restoring moment. So how do we calculate the actual values of this disturbing couple and this restoring couple? Now we know that the length of this bar here is L by 2. So if this angle is theta, then this distance is given by L by 2 sine. Let us say that this angle is delta theta sine delta theta. This is the horizontal distance of the displacement here. And hence the value of this disturbing couple is given as force P into L by 2 sine delta theta. So if we consider that our deformation is small, this sine delta theta will nearly be equal to delta theta. You can get this by performing Taylor series expansion of sine delta theta also, so that our disturbing couple, let us write DC, is given by P L by 2 into delta theta. Similarly, this restoring moment is now given by the product of the rotational stiffness of our spring, which is given as K. Although it is beta r here, we are supposing that our restoring moment is K multiplied by the angle of displacement or angle of deformation of the spring. So our restoring moment Rem is given by K into 2 delta theta. Why 2 delta theta? Because if you look at the diagram, if this is delta theta and again this is delta theta, we know that this total angle will be 2 delta theta, since the sum of the angles of these two sides will be give the sum angle of this exterior angle. You know this property of any triangle. So since this will be 2 delta theta, the total restoring moment in our case will be K into 2 delta theta. Now let us suppose that these restoring forces and this restoring or this disturbing couple and our restoring moment are in equilibrium for this small displacement that we have given, so that now what you can write is PL by 2 delta theta is equal to K into 2 delta theta. This delta theta will be cancelled and you will get the value of P as 4K over L. This situation where the restoring moment is equal to the value of the disturbing couple, this situation will give us that value of load for which this system will be in equilibrium, and that value of load is the critical value of load for this system. Hence we write this P also as P subscript Cr is equal to 4K by L. If you increase the value of axial force P beyond the value of PCR, now this system will go into the state of disequilibrium. So this is the critical load for our system that we have developed here, which value is given by 4K by L. Now what you can say is that if the load that is acting on this system P is less than PCR, our structure will be in the state of equilibrium, and that will be a stable equilibrium, because our system will try to go back to its original position, that is this figure A here. But if the value of P is greater than PCR, then our structure will be unstable and our structure, this column structure, will go into the state of buckling. And you can say what is buckling here? This buckling is the lateral displacement of our column here. So we see that the critical value of the load divides the stable and unstable portion of our structure. That is, this acts as a boundary between the stable equilibrium and unstable equilibrium. So let's summarize what we have discussed here in a diagram in our next slide here. This is a graph between the small deformation that we have given to our column and then the load in the y-axis. For a value of load less than the critical load PCR, or what you can say is for the value of load up to PCR, our structure will be in stable equilibrium. This point B is the point of critical load, and it is also known as the point of bifurcation. This horizontal line that is given here represents the position of neutral equilibrium, because at this point P is equal to PCR, our structure is also in a state of equilibrium, and if the value of load is even increased slightly above PCR, or if the value of the displacement, that is delta theta, is increased, then our structure goes into the state of unstable equilibrium. And this is the line for neutral equilibrium. This is either left or right, because we can displace our structure either to the left or to the right. So this is regarding the equilibrium diagram for buckling of an idealized structure. So you can say that beyond and above this force PCR, our column or our structure will buckle. So the value of PCR, that is the critical load, is some sort of dividing line between the unstable equilibrium and stable equilibrium. As the load is increased beyond the critical load, our structure goes into the state of unstable equilibrium. Why it is called unstable equilibrium? Because this value of theta tends to increase to a higher and higher value as this structure goes further and further away from the initial equilibrium position. That means the tendency of the structure is now not to return to its original position, but rather to assume a shape which is further and further away from the initial equilibrium position. Let us look at this. What is the case of neutral equilibrium in this case? So if this is our column section which is undisplaced at the very beginning, and our load, that is P, is still acting in our column, even when the value of this P is increased beyond the value of PCR, until and unless we give a certain right or left deflection at the center, our structure will rather be in the same equilibrium position instead of deflecting to the left or right. Even when the value of the load is increased beyond the value of the critical load, unless we manually give a small displacement here, this will be our structure state of equilibrium, and that is the state of neutral equilibrium. But if we give a slight displacement here, then this structure will go into the state of unstable equilibrium. So our neutral equilibrium state will not be present for a very long time. So that is why this line is drawn very short and ends here, because beyond this point here, there will be no condition of equilibrium. So this is the end of our introductory lecture here. In our next lecture, we will start with the derivation of Euler's formula for long columns, and then we will go into detail about the buckling of various types of columns. So I will meet you again in next lecture. Till then, keep watching our YouTube channel, keep liking our videos and sharing it among your friends. Stay safe and thank you.